Welcome to Still Science Lab. Tonight, we explore one of the quietest and most unsettling questions in modern physics. What happens when scientists detect something that does not fit the rules? Not a planet drifting where it should not be, not a star behaving strangely in a distant galaxy, but something far smaller, a signal buried inside data, a trace left inside a detector, a possible quantum particle that, according to our best map of reality, should not be there. Deep underground, far from sunlight and the constant noise of the surface, some of the most sensitive instruments ever built are waiting. They sit beneath mountains, inside old mines, under layers of rock and shielding, not because scientists are hiding from the world, but because the world is too loud. Cosmic rays strike the atmosphere. Natural radioactivity whispers from ordinary materials. Electronics produce noise. The human planet is full of interference. And when the thing you are searching for may touch matter only rarely, or exist for less than a blink, silence becomes a scientific tool. So the detectors wait in darkness. They listen for tiny flashes of light, for faint trails of charged particles, for a single nucleus recoiling when something invisible passes through, for energy appearing in a pattern that should not appear. Elsewhere, in great circular tunnels beneath the ground, beams of particles are accelerated to nearly the speed of light. They are guided by magnetic fields, narrowed, focused, and then smashed together in controlled collisions. For a moment, energy becomes matter, and the deep rules of the quantum world reveal themselves in fragments. No one sees a particle directly in the ordinary sense. There is no tiny marble sitting under a microscope. There are only traces, tracks, decays, energy deposits, statistical excesses, missing momentum, signals that must be separated from noise with patience, skepticism, and mathematics. This is how the invisible becomes known. A particle may exist for an instant too short for human intuition to hold. It may decay into other particles before it could ever be isolated. It may interact so weakly that it passes through entire worlds almost unnoticed. But if it leaves the right kind of disturbance, in the right kind of detector, repeated enough times, scientists can begin to ask a dangerous question. Is this just noise? Or is reality trying to tell us something new? When people hear the phrase, a particle that shouldn't exist, it can sound like a violation of nature, as if something has broken through from outside reality or appeared in defiance of the universe itself. But that is not what physicists mean. In science, shouldn't exist does not mean impossible in some absolute sense. It means unexpected. It means that our current theories do not predict it, or do not predict it in that form, or do not explain why it seems to be there. It means a signal has appeared outside the clean lines of the model. A behavior has emerged where the equations expected silence. A pattern in the data does not fit neatly into the catalogue of known particles and forces. That is not magic. It is tension. And tension is where science often begins to grow. Physics has never advanced only by confirming what was already known. It advances when measurement becomes sharper than expectation, when nature produces a result that refuses to disappear, when a small anomaly survives every attempt to explain it away. At first, it may look like an error, a miscalibrated detector, a background event, a statistical fluctuation, a misunderstanding of known physics. Most anomalies are exactly that. They fade, they dissolve under better data, they become reminders that nature is subtle and instruments are imperfect. But sometimes, an anomaly stays, and when it stays, it becomes a doorway. The quantum world is already strange enough without inventing new mysteries. Particles are not little objects moving through space exactly like grains of sand. They are excitations of fields, described by probabilities, interacting through rules that challenge ordinary imagination. An electron can behave like a particle in one experiment and like a wave in another. Empty space is not truly empty. What we call matter is bound up with invisible fields that stretch across the universe. Yet quantum physics is not chaos. It is not a place where anything can happen simply because the rules are strange. In fact, the quantum world is governed by some of the most precise rules ever discovered. The predictions of modern particle physics have been tested again and again with extraordinary accuracy. The known particles are arranged into a framework that has explained an enormous range of experiments. That framework is powerful, but it is not complete. It does not fully explain dark matter, even though dark matter appears to outweigh ordinary matter across galaxies and cosmic structure. It does not include gravity in the same way it includes the other fundamental forces. It does not explain why neutrinos have the masses they do. It does not explain why the universe contains more matter than antimatter, even though the early universe should have treated them almost symmetrically. There are gaps, careful gaps, measured gaps, places where the model works beautifully, but not completely. So when scientists find a signal that seems to point beyond the known particles, they do not immediately announce a revolution. They slow down. They ask what else could imitate it. They test the detector. They question the background. They compare results. They wait for independent confirmation, because in physics, being interesting is not enough. A strange signal must survive. It must survive doubt. It must survive repetition. It must survive the possibility that the universe is simply more complicated in ordinary ways before it can be accepted as something extraordinary. But even before certainty, the mystery matters. Because a possible particle that does not fit the rules forces a deeper question. What are the rules really describing? Our theories are not reality itself. They are maps of reality, built from observation, refined by mathematics, tested by experiment, and limited by what we have been able to measure. A good map can be astonishingly accurate and still not show every road. It can guide us across vast territory and still end at the edge of the unknown. A particle that shouldn't exist is not necessarily a crack in reality. It may be a crack in the map, and that difference is important. Nature is not obligated to match the categories human beings have built. The universe existed long before there were names for electrons, quarks, neutrinos, or fields. It does not become stranger because we discover something new. It was always that way. What changes is our awareness. This is why particle physics carries a strange emotional weight. It asks us to search for the smallest possible signs of a deeper order. A detector waits for a flash so faint it could be mistaken for noise. A collider produces countless events, most of them ordinary, while scientists search for the rare pattern that might reveal something hidden. The entire effort depends on the idea that reality leaves evidence of itself, even when the evidence is almost impossibly small. And sometimes, the smallest evidence points toward the largest questions. A new particle could suggest a hidden field. A hidden field could suggest a new force. A new force could connect ordinary matter to dark matter. Dark matter could explain how galaxies formed and why the universe has the structure we observe. One tiny trace in a detector could belong to a chain of meaning reaching back to the earliest moments after the universe began. That is the scale hidden inside the phrase, a quantum particle that shouldn't exist. It sounds small, but if real, it may not be small in consequence. It could be a clue that matter has a deeper architecture, that the visible universe is only one layer of a larger system. that the particles we know are not the full alphabet of reality, but only the letters we have learned to read so far. Still, the responsible answer remains uncertain. Maybe the particle is real, maybe the data is incomplete, maybe the signal will fade, maybe it will sharpen, maybe the anomaly will become a new discovery, or maybe it will become another lesson in how difficult it is to listen to nature at the edge of measurement. Either way, something valuable happens. The boundary of knowledge becomes visible. That boundary is not a wall, it is a horizon. The closer science gets to it, the more carefully it must move. Every claim must be tested. Every pattern must be challenged. Every possible mistake must be taken seriously. This is not weakness. It is the reason science can change without collapsing. It is the reason uncertainty can become progress. In the quiet of underground detectors, in the controlled violence of particle accelerators, in the patient analysis of data too subtle for human senses, physicists are not only hunting for particles, they are listening for the shape of reality beneath appearance. And perhaps that is why the idea feels so powerful. A particle that should not be there is not merely a scientific puzzle. It is a reminder that the universe may still be deeper than our language, deeper than our instruments, deeper than the theories that have carried us this far. We live in a world that feels solid, ground underfoot, bodies in motion, light from stars, matter arranged into familiar forms. But beneath that familiarity is a quantum structure, quiet and strange, where fields vibrate, probabilities evolve, and particles appear as brief messages from the hidden machinery of existence. Most of the time, the messages confirm what we already know. Sometimes they do not, and when they do not, the universe becomes interesting in the oldest possible way, not because it has broken its own rules, but because we may have found the edge of ours. When physicists say a particle shouldn't exist, they are not saying the universe has made a mistake. The universe does not need permission from human theories. It does not check its behavior against our textbooks. It existed long before we had names for particles, forces, fields, or space itself. So when something appears in an experiment that seems impossible, the problem is not that nature has broken reality. The problem is that our description of reality may be incomplete. That distinction matters. A particle that shouldn't exist is not magic. It is not a supernatural object slipping through a crack in the laws of physics. It is not proof that everything scientists know is wrong. In a careful scientific sense, it means something far more interesting. It means unexpected. It means an experiment may have detected a signal that current theories did not predict. It means a particle may have properties that do not match the known catalogue. It may appear in a place where the model expected nothing. It may decay in a strange way, interact too weakly or too strongly, carry unusual energy, or leave behind a pattern that looks just slightly wrong. Not wrong enough to declare a revolution, but wrong enough to ask questions. And in physics, questions are dangerous in the best possible way. Modern particle physics is built on one of the most successful scientific frameworks ever created, the Standard Model. It describes the known elementary particles and the forces that act between them, except gravity. It tells us how electrons behave, how quarks combine, how forces are carried, and how the Higgs field gives many particles their mass. It has survived decades of experiments. It has made predictions so accurate that they almost seem unreasonable. This is why an unexpected signal matters. It is not appearing in a field of ignorance. It is appearing inside a structure that already works extraordinarily well. If a theory is vague, almost anything can be made to fit it. But the Standard Model is precise. It tells scientists what should happen in particle collisions, how often certain events should appear, and what kinds of particles should be produced under specific conditions. It creates expectations, and because those expectations are so detailed, even a small deviation can become meaningful. A strange particle, or a strange particle-like signal, is not automatically proof of new physics. It is a question mark placed inside one of the most carefully tested maps humanity has ever drawn. That question mark may be temporary. Many have been. Physics is full of anomalies that looked exciting, then faded. A signal can appear because of background noise, detector behavior, imperfect calibration, statistical fluctuation, or an ordinary process that was not fully understood. Sometimes the universe is not revealing something new. Sometimes the instrument is simply more complicated than expected. Sometimes the data needs more time. This is not failure. It is the process. Science grows not by believing every strange result, but by testing it until only the strongest explanations survive. A possible new particle must endure skepticism. It must appear again. It must be measured from different angles. It must remain visible when the data improves. It must survive the long effort to explain it using known physics first. That caution may seem slow from the outside, but it is the reason physics has power. The goal is not to protect old theories at all costs. The goal is to make sure that when a theory changes, it changes for the right reason. A particle that shouldn't exist may be many things. It could be a real new particle, one that belongs to a deeper layer of nature not yet included in the standard model. It could be a messenger from a hidden sector, a part of reality that barely interacts with ordinary matter. It could be connected to dark matter, the invisible mass that shapes galaxies but does not shine. It could point toward a new force, one too subtle to have been noticed in everyday experience. Or it could be none of those. It could be an illusion created by the complexity of measurement. That uncertainty is not a weakness in the story, it is the story. At the edge of knowledge, reality rarely announces itself clearly. It does not say, "Here is a new particle." It does not label discoveries for us. It gives us patterns, traces, probabilities, and deviations. The human work is to decide whether those traces are meaningful. This is why the word shouldn't must be understood carefully. In ordinary language, shouldn't exist sounds absolute. It sounds as if something has violated a law. But in science, laws are not commands imposed on the universe. They are descriptions of patterns we have observed. They are powerful because they work, but they are always open to refinement. Newton's laws were not useless when Einstein changed our understanding of gravity. They remained accurate within a certain range. Einstein did not erase Newton. He revealed a deeper framework. In the same way, a new particle would not necessarily destroy the standard model. It might show where the standard model is incomplete. A map can be accurate and unfinished. That is the right way to think about modern physics. The standard model explains ordinary matter with astonishing success. But it does not explain everything. It does not fully explain dark matter. It does not include gravity as a quantum force. It does not explain why neutrinos have mass in the way they do. It does not explain why the universe contains much more matter than antimatter. It does not answer why the constants of nature have the values they do. So physicists already know the map is incomplete. They just do not yet know what the missing territory looks like. A strange particle could be one of the first landmarks beyond the border, but even that phrase must be used with care. A single anomaly is not a new continent. It is a hint of land through fog. It may be real, or it may vanish when the fog clears. That is why scientists demand more data, stronger statistics, independent confirmation. and a clear explanation of how the signal fits into a wider theory. A discovery is not just something strange. A discovery is something strange that remains true. There is a quiet discipline in that. The most exciting moments in physics are often surrounded by restraint. Scientists may feel the pull of possibility, but they also know how many mysteries have dissolved under better measurement. They have learned not to confuse surprise with certainty, and yet surprise still matters. Because every major shift in science begins as a mismatch between what we expected and what nature did. The atom was once mysterious. Radioactivity was once unexpected. Quantum mechanics itself began from results that did not fit classical physics. Antimatter was once a strange prediction. Neutrinos were once an invisible solution to a missing energy problem. Again and again, reality has forced theory to expand, not by breaking science, by giving science something new to explain. This is the deeper meaning of a particle that shouldn't exist. It is not an ending. It is an invitation. It tells us that our equations may not yet reach all the way down, that the visible world may be connected to hidden structures, that matter, energy, and fields may have relationships we have not yet learned to describe. It also reminds us that human knowledge is provisional but not fragile. A good theory does not fail because one anomaly appears. It becomes stronger if it can explain the anomaly, or more honest if it must be replaced by something deeper. Science is not a statue. It is a living method for correcting itself. That is why uncertainty in physics is not emptiness. It is productive. It is the space where new understanding can form. A strange particle does not automatically prove a new universe. It does not immediately reveal dark matter, a fifth force, or a hidden dimension. It is not a final answer. It is a question mark, and a question mark can be more powerful than a claim when it is placed in the right location. Because the right question can expose the edge of an entire worldview. If the signal is wrong, we learn something about our instruments, our assumptions, or the subtle behavior of known particles. If the signal is real, we may be looking at the first sign of physics beyond the standard model. Either outcome matters. Either outcome refines the map. And perhaps that is what makes the phrase so compelling. A particle that shouldn't exist is really a particle that should not exist according to what we currently know. Those last words are everything. According to what we currently know. They are the boundary between confidence and humility, between knowledge and mystery, between the universe as we have measured it and the universe as it may still be. The most honest science lives at that boundary. It does not rush to believe. It does not refuse to wonder. It waits, measures, doubts, and listens. Because somewhere inside the data, beneath the noise, there may be a signal that survives every test. A small trace of something that does not fit. A particle, or a behavior, or a pattern that asks reality to be described in a wider language. Not proof of magic, not proof that science is broken, but evidence that the universe may still contain structures our best theories have not yet learned to name. The quantum world is not strange because it ignores rules. It is strange because it follows rules that do not resemble the world our senses evolved to understand. At human scales, reality appears solid and direct. Objects occupy places. A stone is here, not everywhere. A door is open or closed. A thrown ball follows a path through the air. Cause and effect seem to unfold in a way that feels almost obvious. We move through a world of surfaces, weights, distances, and clear boundaries, and from that world, common sense is born. But common sense is not a law of nature, it is an adaptation. It is a practical guide for creatures living at a certain size, moving at certain speeds, under certain conditions. It helps us survive in a world of trees, weather, tools, and bodies. But it was never designed to understand electrons, quarks, photons, or the hidden fields beneath matter. At the smallest scales, reality behaves differently. Particles do not act like tiny versions of everyday objects. An electron is not a little planet orbiting an atomic nucleus in the familiar sense. A photon is not simply a tiny glowing bead of light. These words are useful, but they can mislead us if we imagine particles as miniature things, with definite positions, fixed paths, and familiar shapes. In quantum physics, particles can behave like waves. That does not mean they are secretly water waves or ripples in air. It means their behavior spreads out in a way that can interfere, combine, cancel, and produce patterns. A particle can travel through an experiment as if more than one possibility matters at once. It can create an interference pattern, not because it is confused, but because the underlying mathematics of its state allows different possibilities to overlap. Then, when measured, the outcome becomes specific. A dot appears, an energy is recorded, a detector clicks. The strange, spread-out possibility becomes a single event. This is one of the central mysteries of quantum physics. Before measurement, the best description of a particle is not always a definite location or a definite path. It is a probability structure, a set of possible outcomes, each with a certain weight, evolving according to precise mathematical rules. That word, probability, is easy to misunderstand. It does not mean scientists are simply ignorant in the ordinary sense, as if the particle secretly has a definite answer and we just do not know it yet. In quantum theory, probability seems woven into the structure of prediction itself. The theory does not tell us exactly where a single particle will appear in every case. It tells us the pattern that many such events will form, and those patterns are astonishingly accurate. Quantum physics may feel unsettling, but it is not loose speculation. It is one of the most successful frameworks ever built. It predicts the behavior of atoms, light, materials, chemistry, electronics, lasers, semiconductors, and the structure of the microscopic world with extraordinary precision. The modern technological world depends on it, whether we notice that dependence or not. The phone in a pocket, the computer on a desk, the sensors in a spacecraft, the medical tools inside a hospital, all of them rely, in one way or another, on the fact that the quantum world follows rules. Strange rules, but rules. This is why it is misleading to say quantum physics means anything can happen. It does not. The quantum world is not a place where imagination replaces reality. It is not a realm where every possibility is equally real in a careless sense, or where contradictions are allowed simply because things are small. Quantum mechanics is not random chaos wearing scientific language. It is a disciplined theory with sharp constraints, symmetries, conservation laws, and predictions that can be tested. The outcomes may be probabilistic, but the probabilities are not arbitrary. The uncertainty may be real, but it is structured. The strangeness is not a lack of order. It is a deeper kind of order that does not look like everyday experience. Another way to understand the quantum world is through fields. Modern physics does not treat particles as isolated little objects floating in empty space. Instead, particles are understood as excitations of underlying fields. An electron is associated with the electron field. A photon is associated with the electromagnetic field. Other particles arise from other fields. These fields are not optional decorations added to reality. They are part of the fabric of how particles exist and interact. Empty space, in this view, is not simply nothing. It is not a blank stage waiting for matter to enter. It is filled with fields, and those fields can fluctuate, interact, and carry energy. What we call a particle is, in a deep sense, a localized expression of a field, a disturbance, a quantum of excitation, a measurable event arising from something more continuous and less intuitive than a tiny object. This idea changes the emotional texture of matter. The solid world around us begins to look less like a collection of hard pieces and more like a stable arrangement of invisible patterns. The chair, the wall, the body, the air, the planet, all of it is built from quantum fields, interacting according to rules that are hidden from ordinary perception, yet constantly active. The familiar world is the large-scale result of unfamiliar laws. And that is part of what makes unexpected particles so important. If quantum physics were already a place where anything could happen, then a strange new signal would not matter very much. It would be just one more strange thing in a strange world. But quantum physics is not like that. It is precise. It tells us which particles should exist, how they should behave, how they should interact, and what patterns they should leave behind in detectors. So when something appears outside those expectations, it matters. A particle that does not fit is strange even by quantum standards. That is the real significance. The quantum world already allows wave-particle behavior, uncertainty, tunneling, entanglement, and fields that fill space. It already forces us to abandon simple pictures of reality. But within that strangeness, physicists have built an extremely successful order. The known particles are not random. They belong to a pattern. They have properties, mass, charge, spin, ways of interacting, ways of decaying. They fit into a framework. An unexpected particle challenges that framework. It does not challenge it by being weird in a general sense. It challenges it by being weird in the wrong way. It may appear where the theory predicts no particle. It may have a mass that does not fit known families. It may interact too weakly, too strongly, or through a channel that suggests something hidden. It may decay into particles in a pattern that looks unfamiliar. It may leave missing energy in a detector, as if something invisible carried momentum away. Each possibility is a clue, but every clue has to be handled with caution. Because the quantum world is subtle, experiments are difficult, and data can deceive even careful observers. A small statistical fluctuation can mimic a discovery. A background process can look like a new signal. A detector effect can create an illusion. That is why physicists demand repetition, independent confirmation, and enough evidence to separate real phenomena from noise. Still, when an anomaly survives, it becomes powerful. Not because it destroys what came before, but because it may point beyond it. The history of physics is filled with moments when strange behavior revealed deeper structure. Light seemed like a wave, then behaved like particles. Matter seemed like particles, then behaved like waves. Atoms seemed indivisible, then revealed internal structure. Empty space seemed passive, then became a stage of fields and quantum activity. Again and again, nature has been more subtle than the categories we built for it. A new particle would continue that tradition. It would suggest that the known quantum fields are not the full story, that the standard model, for all its precision, may be part of a larger structure, that there may be hidden sectors of matter, unseen forces, or particles that interact so faintly with ordinary matter that they have escaped detection until now. This is where the smallest scales begin to touch the largest questions. A hidden particle might be connected to dark matter, the unseen mass shaping galaxies. A new field might have influenced the early universe. A subtle interaction might help explain why matter survived after the Big Bang instead of annihilating with antimatter. A tiny deviation inside a detector could become a thread leading into cosmology. The quantum world is not separate from the universe. It is the foundation under it. Galaxies, stars, planets, oceans, and living bodies all arise from quantum matter organized over time. The laws governing particles also help shape chemistry, nuclear reactions, radiation, and the behavior of the early cosmos. To understand the very small is not to leave the universe behind. It is to approach the machinery from which the universe is built. And yet, the deeper we go, the less reality resembles intuition. That may be the most humbling lesson of quantum physics. The world that feels obvious to us is not the world in its most fundamental form. What seems solid is mostly structured field and grand forces. What seems definite may emerge from probabilities. What seems empty may be physically active. What seems impossible may simply be outside the range of everyday experience. But none of this means reality is meaningless. It means reality is more disciplined than common sense, more hidden, more mathematical, more surprising. The quantum world does not allow anything to happen. It allows only what its rules permit. But the rules themselves are strange enough to remind us that human intuition is not the final judge of truth. So when scientists search for a particle that does not fit, they are not looking for chaos. They are looking for a deeper order, a new pattern beneath the known pattern, a signal that reveals where the current map ends. And if such a particle is real, it would not be strange because quantum physics is strange. It would be strange because even in a universe already built from probabilities, fields, and invisible interactions, it would still stand out as something nature had kept outside our best understanding. A small disturbance, a trace in data, a question mark at the foundation of matter, and perhaps, beyond it, a wider reality waiting to be named. The search for invisible particles begins with a strange truth. In the deepest experiments in physics, scientists almost never see the thing they are looking for. They see what it leaves behind. A flash of light in a detector, a curved track in a magnetic field, a tiny deposit of energy, a pattern of particles flying away from a collision, a slight imbalance, as if something escaped without being seen. A number in the data that rises above expectation, not dramatically at first, but quietly, persistently, as if reality has left a fingerprint where theory predicted none. Particle physics is, in many ways, a forensic science of the invisible. The particle may already be gone. It may have existed for less than a fraction of a heartbeat. It may have decayed almost instantly into other particles. It may have passed through the detector without touching anything at all. It may have interacted so weakly with ordinary matter that trillions of similar particles could pass through your body every second without leaving a trace you could feel. And yet, under the right conditions, it can leave evidence. That evidence is what scientists follow. In a particle accelerator, researchers do not usually create a new particle and then hold it in place for study. They create extreme conditions. They accelerate known particles to enormous energies and smash them together. In that collision, energy can briefly transform into matter. The event is tiny, but the meaning can be enormous. For a moment, the collision recreates conditions closer to those of the early universe than anything naturally available on Earth. Then everything happens at once. Particles burst outward. Some are stable enough to travel through layers of the detector. Some decay almost immediately. Some leave curved tracks. Some produce showers of secondary particles. Some deposit energy in specialized instruments. Some vanish into particles that cannot be directly detected, leaving only a missing piece in the balance of the event. The detector surrounds the collision like a silent witness. It does not see in the way an eye sees. It measures. It records where energy appeared, how much momentum moved in each direction, which particles curved under magnetic fields, which ones penetrated deeply, which ones stopped quickly, and which combinations of traces might have come from a parent particle that no longer exists. From this evidence, scientists reconstruct the event. It is like arriving after an explosion in a locked room and trying to determine what happened from the marks on the walls, the broken glass, the direction of the debris, and the chemical traces in the air. The original moment cannot be replayed by human senses, but it can be inferred. The invisible becomes visible through consequence. This is one of the most powerful ideas in physics. We know many particles, not because we have ever seen them directly, but because their effects are too consistent to ignore. A particle can be real even if it never becomes an image. Reality does not need to be visible to be measurable. In older detectors, charged particles left tracks in chambers filled with vapor or liquid. Their paths appeared as delicate lines, curving and branching, revealing their charge and momentum. In modern detectors, the process is far more complex. Layers of silicon sensors, calorimeters, magnetic systems, and timing devices collect enormous amounts of information from every collision. Computers process the signals, filter the events, and search for patterns hidden among vast backgrounds of ordinary physics. Most events are not discoveries. Most are expected. Most are the universe doing exactly what known theory says it should do. That is part of the challenge. To find something new, scientists must first understand the ordinary with extraordinary precision. They must know what known particles can produce. They must know how often certain patterns should appear. They must account for detector noise, cosmic rays, material effects, calibration errors, and the countless ways familiar processes can imitate something unfamiliar. A new particle does not usually announce itself with certainty. It begins as a deviation, a small excess of events at a certain energy, a decay happening more often than expected, a distribution that leans slightly away from prediction, a missing energy pattern that seems too consistent to ignore. At first, this is not a discovery, it is a suspicion, and suspicion is where the discipline begins. Physicists ask whether the signal could be noise. They ask whether the detector is behaving correctly. They ask whether the background model is incomplete. They ask whether known particles could create the same pattern through a rare process. They ask whether the statistical evidence is strong enough, or whether the apparent signal might fade as more data is collected, because many signals do fade. This is one of the quiet realities of experimental physics. The path to discovery is littered with almost discoveries, hints that looked promising, bumps in data that seemed meaningful, anomalies that attracted attention only to dissolve under sharper measurement. Nature is subtle, but data is also noisy. When scientists search through enormous numbers of events, chance can sometimes arrange itself into shapes that look important. That is why physics demands patience. A strange pattern must survive. It must survive more data. It must survive independent analysis. It must survive alternative explanations. It must survive the skepticism of people who want the discovery to be real, but know that wanting is not evidence. This caution is not the opposite of wonder. It is what protects wonder from illusion. In deep underground experiments, the same forensic principle applies, but the scene is different. Instead of creating particles in collisions, scientists wait for particles from the universe to come to them. These detectors may search for dark matter, neutrinos, or other weakly interacting particles that pass through ordinary matter almost unnoticed. They are placed underground to reduce interference from cosmic rays and background radiation. The surrounding rock becomes part of the instrument, filtering out noise from the surface world. Inside, the detectors wait for rare interactions. A particle might pass through a tank of liquid and strike an atomic nucleus, causing it to recoil. That recoil might produce a tiny flash of light, a brief release of charge, or a minute vibration. The signal is incredibly small. But if it appears in the right way, with the right energy, and at the right rate, it may point towards something passing through the detector from the hidden universe. Again, the particle itself is not seen, only the disturbance. A whisper in a carefully silenced room. There is something almost philosophical about this. Human beings are built to trust direct perception. We believe what we can see, touch, and hold. But the deeper layers of reality rarely offer themselves that way. The fundamental particles do not sit still for inspection. Many exist only as brief events. Some cannot be isolated. Some are known only through what must have carried away energy or momentum. Physics teaches us that seeing is not the only form of knowing. A footprint can prove an animal passed through a forest. A ripple can reveal something beneath water. A shadow can reveal an object blocking light. A missing piece of energy can reveal a particle that escaped detection. The universe does not always show us the object. Sometimes it shows us the accounting error that only makes sense if the object was there. This is especially important when searching for particles beyond the standard model. If a new particle exists, it may not behave like the particles we already know. It may decay into ordinary matter in rare ways. It may interact weakly. It may carry no electric charge. It may be unstable, hidden, or connected to a sector of physics that barely touches our own. So scientists search broadly. They look for direct traces. They look for indirect effects. They look for unusual decay patterns. They look for missing energy. They look for tiny shifts in how known particles behave. They look for places where the prediction and measurement do not quite agree. This is why particle discovery is often less like finding a new object and more like solving a case. The suspect is gone. The room is full of background noise. The evidence is statistical. Every clue has to be tested against every ordinary explanation, and sometimes, after all that, something remains. A pattern that should not be there, a signal that keeps returning, an excess that grows stronger with more data. At that point, the mood changes. The question is no longer simply, did the detector make a mistake? It becomes, what kind of reality would produce this? That is the moment when physics opens outward. A small deviation can suggest a new particle. A new particle can suggest a new field. A new field can suggest a hidden force. A hidden force can connect to dark matter, the early universe, or the structure of space itself. The trail from a tiny flash inside a detector can lead to questions about why galaxies exist, why matter survived, and what the universe is made of beneath the surface of the visible world. The scale is almost impossible to hold in the mind. A microscopic trace in an instrument, a possible particle that vanished instantly, a clue to cosmic history. But that is how modern physics works. It connects the smallest events to the largest structures. It reads the universe not only through telescopes, but through detectors built to catch fragments of reality too small for sight. There is suspense in this work, but it is not the suspense of sudden revelation. It is slower, more disciplined. A signal appears. Scientists doubt it. The data grows. The analysis deepens. The possibility becomes clearer, or it disappears. Both outcomes matter. If the signal fades, the model becomes cleaner. If it survives, the map of reality changes. Sometimes the evidence is noise. Sometimes it is the first hint of something real. And for a physicist, that boundary is one of the most exciting places to stand, because every known particle was once unknown. Every established feature of reality was once a mystery, a strange effect, a pattern with no explanation. The invisible becomes part of science only when evidence becomes strong enough to carry it from suspicion into knowledge. Until then, the detector keeps listening for flashes, for tracks, for missing energy, for small disturbances in the quiet, for the faint signature of a particle that may be gone before it can be named, but not before it leaves behind enough evidence to suggest that reality is deeper than the world we can see. The first sign of a new particle is rarely dramatic. It does not arrive with a label. It does not announce itself as a discovery. It does not step cleanly into the known catalogue of matter and ask to be named. More often, it appears as something far quieter, a small excess in the data, a decay that happens more often than expected, a strange imbalance in energy, a cluster of events gathered around a certain value, a pattern that should have faded into background noise, but does not. At first, it may not even look like a particle. It may look like a statistical bump, a slight rise in a graph where the known theory predicted a smooth decline. It may look like missing energy, as if something invisible carried momentum away from an event. It may look like an unusual combination of particles appearing after a collision, suggesting that something brief and unstable existed for an instant before transforming into what the detector could record. This is how the pattern begins to break. Modern physics already has a known catalogue of particles. It is not a random list, it is organized. Electrons, quarks, neutrinos, photons, gluons, and the other particles of the Standard Model follow deep mathematical structures. They have properties that can be measured and compared: mass, charge, spin, lifetime, and the ways they interact. They belong to families. They obey conservation laws. They appear in experiments with rates and behaviors that can be predicted with remarkable precision. That is what makes a strange signal meaningful. It is not strange because quantum physics is strange in general. It is strange because it refuses to fit into a system that usually works. A new particle, if it is real, would have to live somewhere in this architecture. It would need a mass, even if extremely small or extremely large. It would need a way to interact, even if that interaction is so weak that ordinary matter barely notices it. It might have no electric charge. It might decay almost instantly. It might be connected to a field we have not yet identified. It might be visible only through what it does to other particles, or through what it prevents them from doing. The possibilities are wide, but not limitless. That is the discipline of physics. A mysterious signal cannot be anything we want it to be. It has to be compatible with data, with conservation laws, with other experiments, with the behavior of known particles, and with the fact that the universe already exists in the form we observe. A new particle is not just an extra object added to reality. It is a new piece in a system where every piece affects the others. This is why physicists are careful. If a detector records something unexpected, the first question is not, have we discovered a new layer of the universe? The first question is, what known process could imitate this? Could the signal come from a background event? Could it be caused by a calibration issue? Could ordinary particles be combining in an unusual but a loud way? Could the detector material itself produce a false signature? Could the mathematics of the analysis be amplifying a fluctuation? Most mysteries in experimental physics begin with restraint. But restraint does not remove the suspense, because sometimes, after every ordinary explanation has been tested, the signal remains. Imagine a collision between particles at enormous energy. For a moment, the collision region becomes a tiny furnace where energy can take the form of matter. Known particles burst outward and leave their traces. Scientists reconstruct the event, compare it with predictions, and repeat the process again and again through billions of collisions. Most of those collisions produce nothing unexpected. Then, in a certain narrow region, there are too many events. Not wildly too many, just enough to matter. A bump appears. If it is noise, it will fade as more data arrives. If it is real, it may sharpen. It may begin to look less like randomness and more like the footprint of something unstable, something created in the collision and then gone almost instantly. The particle itself may never be directly observed, but its decay products could point backward, like fragments from an object that existed too briefly to hold. This is the forensic logic of particle physics. The particle is the missing cause. The data is the evidence, the theory is the map, and the anomaly is the place where the map and the evidence no longer agree. A pattern-breaking particle could appear in many forms. It might show up as an unexpected decay pattern, where a known particle breaks apart in a way that happens more often than predicted. It might appear as missing energy, suggesting that something invisible escaped the detector. It might emerge from high-energy collisions as a resonance, a temporary state that reveals itself only through the particles it becomes. It might be connected to hidden matter, part of a dark sector that interacts with ordinary matter through only the faintest channels. That last possibility is especially powerful. Most matter in the universe may not be the kind of matter we are made of. Galaxies rotate as if they contain far more mass than their stars and gas can explain. Clusters of galaxies bend light more strongly than visible matter alone should allow. The large-scale structure of the cosmos appears shaped by an unseen gravitational presence. We call it dark matter, but the name is more confession than explanation. We know what it does. We do not yet know what it is. If a new particle were connected to dark matter, it would not just add one item to a list. It could begin to explain why galaxies hold together, why cosmic structures formed the way they did, and why the visible universe is only part of the full story. A tiny signal inside a detector could become a clue to the invisible scaffolding of the cosmos. That is why the stakes are so high. A particle outside the known pattern could suggest that the standard model, powerful as it is, describes only the visible surface of a deeper theory. The known particles may be one layer of reality. Beneath them, or beside them, there may be fields and interactions that have remained hidden because they barely touch ordinary matter, not because they are unreal, because they are quiet. Physics has found hidden things before. The neutrino was proposed because energy seemed to be missing in certain radioactive processes. For a long time, it was almost ghost-like, necessary to explain the data, but extremely difficult to detect. Eventually, the ghost became part of the known universe. What began as a missing piece became a particle. A pattern-breaking signal today could be similar, or it could vanish. That uncertainty is essential. A mysterious bump in collision data is not automatically a new particle. An unusual decay is not automatically a new force. A missing energy event is not automatically dark matter. Science becomes reliable precisely because it refuses to leap from mystery to conclusion. The signal must grow stronger. It must be confirmed independently. It must be tested against every known possibility. But while the verdict remains open, the question is alive. What kind of particle would produce this? What properties would it need? Would it have mass, unlike any known particle? Would it carry no familiar charge? Would it interact through a force we have not measured before? Would it decay into ordinary matter or vanish into something hidden? Would it solve one mystery while creating several more? This is how a possible discovery changes the atmosphere of physics. It does not provide certainty at first. It creates a space of possibility. The known catalogue begins to feel less final. The standard model, once complete in appearance, begins to look like a framework with shadows at its edges. And shadows matter, not because they prove what is hidden, but because they tell us where to look. A new particle would also raise a deeper question. Why does it have the properties it has? In physics, mass, charge, spin, and interaction are not decorative features. They determine how a particle behaves, what it can become, what it can touch, what forces it feels, and what role it may have played in the history of the universe. If a particle is heavy, it may require extreme energy to create. If it is light, it may have shaped cosmic evolution. If it is stable, it may still fill the universe. If it decays quickly, it may leave only brief traces. If it interacts weakly, it may pass through ordinary matter almost unseen. Each property is a clue, and together they form a biography. Not a biography of life, but of existence. How the particle appears, how it disappears, what it can influence, where it belongs in the deep structure of matter. This is why a particle that breaks the pattern is so different from an ordinary unknown. It does not merely fill an empty slot. It may reveal that the slots themselves were not complete. It may show that the familiar families of particles are part of a larger arrangement. It may point towards symmetry hidden at high energy, or a field that shaped the early universe, or a connection between matter and dark matter that has been invisible until now. The smallest deviations can carry enormous meaning. A tiny excess in a detector may seem disconnected from human life, but it reaches into the foundations of everything familiar. The atoms in our bodies, the light from stars, the chemistry of planets, the formation of galaxies, all depend on particle physics. If there is a deeper layer beneath the known one, then the universe we experience is built on something we have not yet fully understood. That does not make reality unstable. It makes it unfinished in our minds. The universe is not changing because we discover a new particle. It was always what it was. What changes is the map. A region once blank begins to gain structure. A mystery becomes measurable. A signal becomes a candidate. A candidate becomes, if it survives, a discovery. Until then, the particle remains suspended between noise and revelation. A strange pattern, a possible trace, a question written in data. Maybe it is nothing. Maybe it is an error waiting to be corrected. Maybe it is a rare known process wearing an unfamiliar mask. Or maybe it is the first sign of a deeper order, a particle outside the catalogue, a small disturbance in the known pattern of reality. That is the tension at the heart of the search. The universe does not always reveal itself through grand events. Sometimes it speaks through excess counts, decay angles, missing energy, and the quiet refusal of data to behave exactly as expected. Sometimes the first hint of a new layer of physics is not a dramatic discovery, but a pattern that will not go away. And if that pattern holds, then the particle that should not be there becomes something else. Not an impossibility, not a violation, but a message, a sign that the known particles may not be the full alphabet of matter, and that beneath the structure we have already named, reality may still contain letters we have only just begun to detect. The standard model matters because it is not just another theory in physics. It is the most precise map we have of the visible building blocks of reality. Every solid object, every breath of air, every drop of water, every cell in a living body, every planet, star, and cloud of glowing gas is made from particles whose behavior is described at the deepest known level by this framework. It tells us what ordinary matter is made of. It tells us how particles interact. It tells us how forces are carried through fields. It tells us why atoms can exist, why light can be emitted and absorbed, and why the universe has enough structure for chemistry, stars, and life. It is one of the greatest achievements in the history of science, and yet it is not complete. That tension is what makes it so important. The Standard Model describes the known elementary particles and three of the fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It includes the matter particles that make up atoms, such as quarks and electrons. It includes neutrinos, ghost-like particles that pass through matter with almost no resistance. It includes force carriers, particles associated with the interactions that hold matter together or allow it to transform. And it includes the Higgs field, whose discovery helped explain why many particles have mass. For decades, experiments have tested this framework with astonishing precision. Particle accelerators have smashed matter together at enormous energies, and the results have matched the predictions again and again. Detectors have recorded collision patterns, decay products, energy deposits, and particle tracks, and the Standard Model has remained standing. It has predicted particles before they were found. It has explained processes too small and fast for human senses. It has turned the invisible machinery of matter into something measurable. This is why physicists do not discard it casually. The Standard Model works. It works so well that any new theory must explain why it works. A deeper framework cannot simply replace it by saying it was wrong. It must reproduce its success while extending beyond it. In the same way that Einstein's theory did not make Newton useless, but showed where Newton's laws were part of a larger picture, any future physics must preserve the Standard Model's victories while revealing its limits. And the limits are real. The Standard Model describes ordinary matter beautifully, but ordinary matter is not the whole universe. In fact, it appears to be only a small part of the cosmic inventory. Galaxies rotate as if they contain far more mass than we can see. Clusters of galaxies bend light more strongly than visible matter can explain. The large-scale structure of the universe suggests the presence of an invisible substance that interacts gravitationally but does not shine. We call it dark matter. The Standard Model does not tell us what dark matter is. That is not a small missing detail. Dark matter appears to shape galaxies and cosmic structure on the largest scales. It may outweigh the ordinary matter described by the Standard Model by a wide margin. And yet, if it is made of particles, those particles are not part of the known catalogue. Somewhere beyond the model, something may be missing. Then there is dark energy. The universe is not only expanding, its expansion is accelerating. Something appears to be driving space apart on cosmic scales, something that behaves unlike ordinary matter or radiation. The Standard Model does not fully explain this. It describes quantum fields with extraordinary power, but the relationship between those fields and the energy of empty space remains one of the deepest unsolved problems in physics. And gravity remains outside the framework. The Standard Model is a quantum theory of particles and fields. Gravity, our best description of it, comes from general relativity, where mass and energy curve space-time itself. Both theories are enormously successful in their own domains, but they do not merge easily. At the heart of black holes, in the earliest moments of the universe, and at scales where quantum effects and gravity both matter, our understanding becomes incomplete. The universe appears to be telling us that two of our greatest theories are not yet part of a single language. Neutrinos add another mystery. They are included in the Standard Model, but their masses do not fit naturally into its simplest original form. Neutrinos are extremely light, and they can change identity as they travel, a behavior that implies mass. That discovery was a major clue that the Standard Model, though powerful, needed modification. Neutrinos are not errors in the map, but they reveal that the map has edges. And then there is one of the oldest cosmic questions. Why is there something instead of almost nothing? The early universe should have produced matter and antimatter in nearly equal amounts. When matter and antimatter meet, they can annihilate into radiation. If the balance had been perfect, the universe might have ended up filled mostly with light, with very little matter left behind to form stars, planets, or bodies. But clearly, matter survived. The Standard Model contains some differences between matter and antimatter, but not enough to explain the universe we see. Something tipped the balance. Something allowed matter to remain. And without that imbalance, none of this would be here. No galaxies. No Earth. No observers asking why matter exists. These are not minor puzzles. They are major signs that the Standard Model, for all its elegance and success, is not the final story. It is a remarkably accurate structure, but it does not cover the whole landscape. This is why a particle that does not fit the Standard Model would matter so deeply. It would not automatically prove that everything we know is wrong. That is too simple. The known theory has earned its place through decades of precise tests. A new particle would not make electrons vanish or atoms stop behaving as they do. It would not erase the predictions that already work. But it could reveal that the Standard Model is part of something larger. A strange particle could be like a crack in the wall, not a collapse, a crack, a place where light comes through from the other side. That crack might lead to dark matter. It might point toward a hidden sector of particles that barely interact with ordinary matter. It might reveal a new force, one too subtle to have appeared in everyday experience. It might help explain neutrino masses, matter-antimatter imbalance, or the conditions of the early universe. It might open a door into physics that has been present all along, but hidden behind the success of the theory we already had. This is the strange position of modern physics. We know more about matter than any previous civilization could have imagined. We can predict the behavior of particles with extraordinary accuracy. We can build machines that test nature at energies and sensitivities far beyond ordinary experience. We can detect particles that exist for almost no time at all and infer invisible processes from traces in data. And yet, the largest features of the universe still tell us that something is missing. The galaxies know something, the Standard Model does not. The expanding universe knows something it does not. Neutrinos know something it does not. The existence of matter itself may know something it does not. That is why the search continues. Not because the Standard Model has failed, but because it has succeeded so well that its unanswered questions have become impossible to ignore. A weak theory leaves confusion everywhere. A strong theory reveals exactly where the mystery remains, and the Standard Model is strong enough to show us its own limits. That is a rare kind of success. It gives physics a foundation solid enough to stand on, but not so final that inquiry ends. It tells us the known particles follow a deep order, but it also leaves open the possibility that this order is part of a larger pattern. It lets us ask sharper questions than we could have asked before. If dark matter exists as particles, why have we not found them? If gravity is quantum, what carries its deepest structure? If neutrinos have mass, what gives it to them? If matter survived the early universe, what broke the symmetry enough to let stars and planets form? If a new particle appears, where does it belong? These questions are not signs that physics is broken. They are signs that physics is alive. Science grows in the space between what works and what remains unexplained. The Standard Model is not a finished cathedral with no doors. It is more like a vast, illuminated structure built inside a larger darkness. Its walls are strong, its architecture is precise, but here and there, the measurements suggest there may be passages beyond it. A particle outside the known catalogue would be one of those passages. It would be evidence that the wall has a hidden door. And hidden doors are powerful things in science. They do not destroy the rooms we already understand. They expand the building. They show that what looked complete was actually connected to something larger. That is the right way to think about a particle that should not exist. Not as proof that reality has broken, not as proof that the Standard Model was useless, but as a possible sign that the universe has more layers than the visible ones. That matter has deeper structures. That forces may exist beyond those we have named. That the history of the cosmos may require particles and fields still waiting outside the known map. The Standard Model matters because it is the best description we have of the particles and forces that make up ordinary reality. Its incompleteness matters because reality is not limited to what is ordinary, and somewhere in the gap between those two truths, a strange new particle could change the direction of physics, not by tearing down the wall, but by showing where to open it. A new particle would be extraordinary on its own, but in physics, a particle is rarely just a particle. It may be a sign of a deeper interaction, a messenger, a carrier, a clue that matter is not only made of hidden ingredients, but connected by hidden rules. If an unexpected signal appears in an experiment and refuses to fit the known catalogue, one of the most important questions scientists ask is not only what is it, but what does it communicate? Because, in the quantum world, particles and forces are deeply connected. The universe is not built from isolated pieces drifting through emptiness. Matter interacts. It attracts, repels, transforms, decays, binds, scatters, and radiates. Those interactions are what make structure possible. Without them, particles would not form atoms. Atoms would not form molecules. Stars would not burn. Light would not carry information. The world would not have chemistry, warmth, or complexity. Forces are the grammar of reality. They determine how the letters can be arranged. Known physics describes a small set of fundamental interactions. Electromagnetism governs light, electricity, magnetism, and the structure of atoms. It is the reason electrons bind to nuclei, the reason chemistry exists, and the reason nearly everything we touch feels solid. The strong nuclear force binds quarks together inside protons and neutrons and holds atomic nuclei together against the repulsion of electric charge. The weak nuclear force allows certain particles to transform into others, powering forms of radioactive decay and playing a crucial role in the nuclear processes of stars. Gravity shapes planets, stars, galaxies, and the large-scale architecture of the cosmos. These forces are not optional details added to matter. They are the relationships that make matter meaningful, but the list may not be complete. That possibility is one of the quiet tensions beneath modern physics. The known forces describe an enormous range of phenomena, from the structure of atoms to the motion of galaxies, and yet, the universe still contains mysteries that seem to point beyond the visible system. Dark matter shapes galaxies, but does not appear to interact with light. Dark energy drives cosmic acceleration, but its nature remains unknown. Neutrinos behave in ways that suggest physics beyond the simplest version of the Standard Model. Gravity itself has not been fully united with quantum theory, so physicists ask a dangerous but reasonable question. What if there are other forces, not forces that replace the known ones, not forces that show up in everyday life as something obvious, but subtle interactions, hidden from ordinary matter, perhaps operating mainly in sectors of the universe we do not yet understand? A new particle could be the first sign of such a force. In modern particle physics, forces are often associated with messenger particles. The electromagnetic force is carried by photons. The strong force is associated with gluons. The weak force has its own heavy carriers. These particles are not messengers in the human sense, but they allow interactions to happen. They carry the influence of one particle to another through underlying fields. So if scientists found a new particle that does not fit the known pattern, one possibility is that it might be a messenger of a hidden interaction, a signal from a hidden sector. A hidden sector is a phrase physicists use for a possible part of reality that contains particles and forces beyond the standard model, but interacts only weakly with the particles we know. It may be all around us and still remain nearly invisible, not because it is far away, but because it barely communicates with ordinary matter. That idea can feel strange, but it is not unreasonable. We already know of particles that are difficult to detect. Neutrinos pass through matter with astonishing ease. Dark matter, if made of particles, may be passing through Earth constantly without producing light or sound or heat in any ordinary way. The absence of obvious interaction does not mean absence of existence. It may simply mean the connection is faint. A hidden force would be even more subtle. It might not move planets in a visible way. It might not alter chemistry under normal conditions. It might not produce light our eyes can see. Instead, it might reveal itself through rare decays, tiny shifts in particle behavior, missing energy in collisions, or unexpected signals in carefully shielded detectors. This is how a new grammar of reality might first appear, not as a thunderclap, as a small violation of expectation. If particles are like letters in the alphabet of reality, then a new force would be like discovering a new grammar. The letters alone tell us what exists. The grammar tells us how those things can relate. It tells us what can combine, what can transform, what can remain stable, and what can influence what. Discovering a new particle would be like finding an unfamiliar symbol. Discovering a new force would mean learning that the symbol belongs to a deeper language. That is why the possibility is so powerful. A new force could change not only the list of particles, but the structure of the theory that connects them. It might help explain dark matter. For decades, dark matter has been known through gravity. Galaxies rotate too quickly for their visible matter alone. Clusters of galaxies behave as if unseen mass is present. Light bends around cosmic structures more strongly than ordinary matter can explain. The evidence is vast, but indirect. We know dark matter pulls with gravity. We do not know whether it also feels forces hidden from us. Perhaps dark matter is not a single particle, but an entire hidden world. It may have its own interactions, its own fields, its own structure. Maybe dark matter particles can attract or repel each other through a dark force. Maybe they form complex behavior without emitting ordinary light. Maybe their connection to ordinary matter is so weak that we have only glimpsed them through gravity and rare experimental hints. A new particle could be a bridge. It might interact faintly with ordinary particles and strongly with hidden ones. It might be the mediator between the visible universe and the dark sector. It might be the small opening through which two parts of reality exchange information. That does not mean this is what any current anomaly must be. Science cannot leap from mystery to conclusion. A strange signal is not automatically a hidden force. It may be a background effect. It may be a statistical fluctuation. It may be ordinary physics in a difficult disguise. The history of particle physics is full of hints that faded when more data arrived. Any claim of a new force would require extraordinary care, repeated tests, and independent confirmation. But the possibility remains important, because forces define the universe at every scale. Electromagnetism lets atoms form and light travel. The strong force makes atomic nuclei possible. The weak force allows stars to change matter in their cores. Gravity gathers gas into stars and stars into galaxies. If another force exists, even a subtle one, it could have shaped the early universe in ways we have not yet recognized. It could have influenced which particles survived after the Big Bang. It could have helped determine the abundance of dark matter. It could have left faint fingerprints in cosmic structure, particle decays, or high-energy collisions. A hidden force would not just be a new item in a physics textbook. It would be a new relationship woven into reality. And relationships matter. A universe made only of particles without forces would be a universe without structure. Particles would exist, but nothing would bind them into atoms, ignite them into stars, or arrange them into living systems. Forces turn existence into behavior. They turn ingredients into patterns. This is why physicists care so deeply about unexpected particles. A particle that breaks the pattern may be more than an object. It may be evidence of a missing interaction, a doorway into a sector of physics that has remained quiet, not because it is small, but because it does not speak loudly to our detectors. The hidden sector, if it exists, may be like a room next to ours separated by a thick wall. We do not see inside it. We do not hear ordinary activity there. But if a faint vibration passes through the wall, or if a tiny crack allows one signal to cross, we might begin to infer the existence of a larger space beyond our own. That is the role a new messenger particle could play, a vibration through the wall, a brief transmission, a particle that appears where no known force should have produced it. The mystery would then become larger. What field does it belong to? What particles does it connect? Why has it remained hidden? Did it matter in the early universe? Does it still influence dark matter today? Could it explain one of the gaps in the standard model? Or would it open even deeper questions? Often, the most important discoveries do both. They solve one mystery and reveal several more. That is not a flaw. That is how physics deepens. The discovery of electromagnetism did not end questions about light. It opened a path to relativity and quantum theory. The discovery of the atomic nucleus did not complete matter. It revealed protons, neutrons, quarks, and the forces that bind them. The discovery of neutrino mass did not close the story of neutrinos. It suggested physics beyond the simplest known model. A new force would likely be the same, not an ending, an opening. It would tell us that the universe has been more connected than we realized, that some part of reality has remained hidden not because it is unreal, but because our instruments have only recently become quiet enough, powerful enough, or patient enough to notice its faint effects. There is a controlled kind of mystery here, not fantasy. Not anything can happen, but a recognition that the known forces, for all their success, may not exhaust the possibilities of nature. The universe is under no obligation to limit its interactions to the ones most visible to human beings. We evolved inside a narrow band of conditions, made of ordinary matter, sensitive to ordinary light, living under gravity and chemistry. It would be surprising, almost arrogant, to assume that our familiar interactions are the whole language of existence. A new particle could challenge that assumption. It could be a messenger, a carrier of influence from a hidden field. a sign that matter has relationships we have not yet named. And if that is true, then the discovery would not simply add a new dot to the map. It would add new lines between the dots, new rules, new pathways, new reasons why the universe became what it is. The alphabet would expand. But more importantly, the grammar would change. And somewhere in that change, physics would move closer to the deeper structure beneath reality, not just what exists, but how existence speaks to itself. The smallest things in the universe may hold the key to the largest mysteries. That is one of the strange reversals at the heart of modern physics. When we want to understand galaxies, the early universe, dark matter, and the origin of cosmic structure, we might expect to look only outward toward deep space, ancient light, and the enormous architecture of the cosmos. And we do look there. Telescopes measure galaxies billions of light years away. Observatories map the faint afterglow of the early universe. Astronomers trace how matter gathers into filaments, clusters, and vast cosmic walls. But to understand why the universe looks the way it does, we also have to look inward, into matter, into fields, into particles so small they cannot be seen directly. Because the universe did not begin with galaxies. It did not begin with stars, planets, oceans, or atoms in the familiar sense. The early universe was hot, dense, and extreme. It was a place where particles and radiation dominated reality, where the rules of quantum physics were not hidden beneath everyday matter, but written across the entire cosmos. Before there were stars, there were particles. Before there were galaxies, there were interactions. Before there were planets, there were fields cooling, breaking symmetries, forming matter, and leaving behind the conditions from which everything else would grow. This is why a possible new particle matters far beyond the detector that finds it. A tiny signal in a laboratory may connect to events that happened when the universe was young. A particle that appears for a fraction of an instant in a collision may resemble particles that once filled space in enormous numbers. A weak interaction measured underground may point toward invisible matter shaping galaxies across billions of years. The small and the large are not separate. They are different chapters of the same story. Dark matter is the clearest example of this connection. Across the universe, galaxies behave as if they contain much more mass than we can see. Stars orbit too quickly around galactic centers. Clusters of galaxies hold together with more gravity than visible matter can provide. Light from distant objects bends around cosmic structures as if invisible mass is present. Something is there. Something gravitational. Something that does not shine. We call it dark matter, but the name is not an explanation. It is a label for an absence in our understanding. Dark matter is not dark because it is black like smoke or shadow. It is dark because it does not emit, absorb, or reflect light in the ordinary way. It does not reveal itself through telescopes the way stars and gas do. It reveals itself through gravity. The great question is what dark matter is made of. One possibility is that it consists of particles we have not yet discovered. These particles might barely interact with ordinary matter. They may pass through planets, stars, detectors, and bodies almost unnoticed. They may not feel electromagnetism, which means they would not produce light. They may not form atoms. They may not collide often. They may exist all around us, flowing through the galaxy, invisible except through their gravitational pull. A particle like that would be difficult to find, but not impossible. If it occasionally interacts with a detector, it might leave a tiny recoil, a flash of light, a small deposit of energy. If it can be produced in a particle accelerator, it might escape without being seen, leaving behind missing energy. If it affects known particles indirectly, it might shift a measurement ever so slightly away from expectation. A strange particle that barely touches ordinary matter could be more than a laboratory curiosity. It could be a clue to the missing mass of the cosmos. That possibility creates a bridge between two very different kinds of science. On one side, cosmologists map the universe on the largest scales, measuring galaxies, gravitational lensing, and the cosmic background radiation. On the other side, particle physicists search for tiny interactions in detectors and collisions. One field studies the universe as a whole, the other studies the smallest ingredients of matter. But the mystery may be the same. The dark matter holding galaxies together may be made of particles. The particles hiding in detectors may be part of the cosmic structure above us. A signal in a laboratory could explain why galaxies did not fly apart. The early universe deepens that connection. In its earliest moments, the universe was an extreme environment, unlike anything we can recreate completely. Temperatures and densities were enormous. Particles were constantly being created, destroyed, transformed, and scattered. Forces that appear separate today may have behaved differently under those conditions. Fields that now seem quiet may have shaped the expansion, cooling, and composition of everything that followed. A particle that seems rare today might have been common then. A particle that is difficult to produce in modern experiments might have formed naturally in the early universe, when energy was everywhere. A hidden field might have influenced how matter formed, how dark matter survived, or why one kind of matter remained when antimatter nearly cancelled it out. This is one of the deepest problems in cosmology. The universe contains matter. That sounds obvious, but it is not trivial. In the early universe, matter and antimatter should have been produced in nearly equal amounts. When they meet, they annihilate into radiation. If the balance had been perfect, almost all matter could have disappeared, leaving behind a universe filled with light, but without galaxies, planets, or life. But matter survived. Something tipped the scale. The known laws contain some differences between matter and antimatter, but not enough to explain the abundance of matter we observe. A new particle or a new interaction could have played a role in that imbalance. It might have behaved differently with matter and antimatter. It might have opened a pathway that allowed ordinary matter to remain. It might have influenced the conditions that made a material universe possible. If so, then a particle that appears strange in a detector would not simply be an addition to physics. It could be connected to the reason anything made of matter exists at all. That is a remarkable thought. The same kind of hidden particle that barely interacts with ordinary matter today may have helped shape the early universe. The same physics that appears as a tiny anomaly in experimental data may have affected the formation of galaxies. The same unseen ingredient that avoids light may provide the gravitational scaffolding on which cosmic structure was built. The universe we see may depend on particles we have not yet named. Galaxies did not form randomly from a smooth cloud. They grew from tiny variations in density, amplified by gravity over cosmic time. Dark matter, because it does not interact with light the way ordinary matter does, could begin gathering into structures early, forming gravitational wells. Ordinary matter later fell into those wells, cooling, forming stars, and eventually building galaxies. Without dark matter, galaxy formation would look very different. The universe might not have developed the same structure. The Milky Way might not exist as it does. The chain leading to the sun, earth, chemistry, and life might have unfolded differently or not at all. So the search for dark matter particles is not just a search for missing mass. It is a search for part of the story of how the cosmic web formed. It is an attempt to understand why the universe became structured instead of remaining a thin, diffuse sea of particles and radiation. This is where the emotional scale of the question changes. A particle sounds small, almost insignificant. A thing too tiny to see, too brief to hold, too subtle to notice without enormous machines and years of analysis. But in physics, small does not mean unimportant. The smallest rules can govern the largest outcomes. The mass of a particle, the strength of an interaction, the stability of a hidden state, the way a field behaved when the universe was young. These details can echo across billions of years. A slight imbalance becomes matter. A hidden particle becomes dark matter. A quantum fluctuation becomes cosmic structure. A microscopic rule becomes a galaxy. That is one of the most beautiful and humbling ideas in science. The universe is connected across scale. The behavior of the smallest things can shape the destiny of the largest. The particles inside atoms and the galaxies beyond sight are not separate realms. They are linked by laws that operate everywhere. This is why scientists build particle detectors underground and launch telescopes into space. They are not doing unrelated work. They are approaching the same mystery from opposite directions. One listens for rare interactions in silence. The other gathers ancient light from the edge of the observable universe. Between them lies the question of what reality is made of and how it became this way. A new particle could become the missing link. It might not be dark matter itself. It might be connected to dark matter. It might be a mediator between ordinary matter and a hidden sector. It might be a remnant of early universe physics. It might be a clue that points toward a larger theory, one that explains particles and cosmology in a single framework. Or it might be a false signal. That possibility must remain. Science does not become deeper by forcing every anomaly into a grand story. It becomes deeper by letting evidence decide which stories survive. A strange particle must be confirmed. Its properties must be measured. Its connection to cosmology must be tested. The universe is too subtle for certainty without discipline. But the possibility is enough to keep the question alive. Because if the particle is real, it may reveal that the boundary between the microscopic and the cosmic was never a boundary at all. It may show that the dark matter shaping galaxies is part of a hidden particle world. It may show that the early universe left behind relics we are only now learning to detect. It may show that the missing pieces of cosmology are not only written in the sky, but buried in the quiet traces of matter itself. The smallest thing in the universe may reveal something about the entire universe. A signal in a detector may point to the invisible mass around galaxies. A particle born in an accelerator may resemble something that existed when the cosmos was young. A barely interacting field may have helped decide why matter survived, why galaxies formed, and why there is a world beneath our feet instead of only radiation fading through space. That is the bridge. From the quantum to the cosmic, from a trace too small for human senses to the architecture of the universe. From a particle that seems out of place to the possibility that reality has hidden layers connecting every scale of existence. And somewhere along that bridge, science keeps listening not only for what matter is, but for what the universe has been trying to tell us since the beginning. The most important question in a moment of scientific excitement is often the least dramatic one. What if the discovery is wrong? Not wrong because scientists were careless. Not wrong because the universe is misleading on purpose. But wrong in the ordinary, difficult, deeply human sense that a signal can appear meaningful before it has been fully understood. A trace in a detector can look like the first sign of new physics. A bump in the data can seem like the edge of a hidden particle. A strange decay can feel like the universe has opened a door. And then, with more data, the door disappears. This has happened many times in physics. It will happen again. That is not a failure of science. It is science working exactly as it should. A possible particle that shouldn't exist begins its life under suspicion. It has to. The history of discovery is also a history of false alarms, incomplete measurements, backgrounds that were not fully understood, detector effects that mimicked something new, and statistical fluctuations that briefly arranged themselves into the shape of a mystery. In particle physics, the data is vast. Experiments may record billions or trillions of events. Most of them are ordinary, most are expected. Somewhere inside that ocean of information, scientists search for small deviations from prediction. But when the search is that large, chance has room to create illusions. A random rise in one region, an unusual cluster of events, a pattern that looks suggestive, but only because so much data has been examined. The human mind is very good at noticing patterns. Science has to ask whether the pattern is real. That is why caution is not a lack of imagination. It is the discipline that keeps imagination connected to reality. Without caution, every anomaly becomes a revolution. Every unexplained signal becomes a new particle. Every statistical bump becomes evidence of a hidden universe. That may be exciting for a moment, but it would make knowledge weaker, not stronger. Physics earns trust because it resists its own excitement. When an unexpected signal appears, scientists first try to destroy it. They test the detector. They question the calibration. They examine the background. They ask whether known particles could have produced the same signature through a rare process. They look for hidden biases in the analysis. They divide the data in different ways. They compare different methods. They ask whether the signal remains when the experiment is treated with every reasonable doubt. Only a strong result survives that process. Many do not. Some strange signals turn out to be detector errors. A sensor may respond differently than expected. A material inside the experiment may produce a background no one fully accounted for. Electronics may introduce noise. Timing systems may drift. A rare interaction with the surrounding environment may imitate the thing researchers are searching for. Some signals are background noise. The universe is full of ordinary processes that can hide inside extraordinary searches. Cosmic rays, radioactive decay, neutrinos, secondary particles, scattered radiation, and known particle interactions can all leave traces. In a sensitive detector, nothing is ever perfectly silent. The challenge is not only to hear a whisper, but to know which whisper came from what. Some signals are statistical fluctuations. This is one of the hardest ideas to communicate, because a fluctuation can look real for a while. If a theory predicts a certain number of events, and the detector sees slightly more, the excess may feel like a clue, but random variation can produce small excesses. With enough measurements, some regions of data will rise above expectation simply by chance. The question is whether the excess grows stronger as more data arrives. A real signal should become clearer. A fluctuation usually fades. Some signals come from misunderstood known physics. This may be the most interesting non-discovery of all. Sometimes an anomaly does not reveal a new particle, but it does reveal that an ordinary process was more complicated than scientists realized. The unexpected result still teaches something. It sharpens the model, it improves the experiment, it forces better calculations. It turns uncertainty into refinement. In that sense, even a wrong discovery can be useful. The particle may not exist, but the search leaves physics better than before. This is why the disappearance of a strange signal should not be treated as embarrassment. It is part of the filtering process by which science separates reality from possibility. A claim enters the world as a candidate. It is tested, attacked, repeated, and compared. If it fails, it is removed. If it survives, it becomes more serious. A particle that shouldn't exist must survive skepticism before becoming reality. That skepticism is not hostility. It is the price of admission. Extraordinary claims require repeated tests. One experiment may find a hint, but a hint is not enough. Another detector should look for the same effect. Another group should analyze the data. A different method should test the same idea. The signal should appear where it is expected, and not appear where it should not. Its properties should become measurable. Its behavior should fit into a consistent explanation. Independent confirmation matters because no single experiment is perfect. Every instrument has its own weaknesses. Every analysis has assumptions. Every collaboration has blind spots, no matter how careful. But if different instruments, different teams, and different methods begin pointing toward the same result, the case becomes stronger. Nature may be subtle, but it is not supposed to depend on one fragile interpretation. Strong statistical evidence matters too. Physicists do not want a signal that merely looks interesting. They want to know how likely it is that the result could have appeared by chance. They want confidence that the pattern is not a temporary arrangement of noise. This is why discoveries in particle physics often require extremely high standards of evidence before being announced as discoveries. The bar is high because the consequences are high. A new particle would reshape theory. It could imply a new field, a hidden force, a path toward dark matter, or physics beyond the standard model. It would demand explanation from the deepest frameworks we have. A claim that powerful cannot rest on a weak signal. It must be earned. This can make science seem slow, but slowness is not always weakness. Sometimes slowness is the speed of honesty. The universe does not become less mysterious because scientists are careful. It becomes more meaningful. A mystery that survives careful testing is stronger than a mystery protected from doubt. A discovery that has passed through skepticism carries a different weight. It is no longer just exciting, it is reliable. This is the deep strength of science. It doubts itself. Most human belief systems defend themselves by resisting contradiction. Science does something stranger. It invites contradiction in controlled ways. It builds experiments specifically designed to test whether its own ideas fail. It accepts that even successful theories are provisional. It understands that every model is a map, and every map can be improved. That does not make science uncertain in a shallow sense. It makes science self-correcting. Theories are not discarded because someone dislikes them. They are challenged by measurement. Ideas are not accepted because they sound profound. They must make contact with evidence. Claims are not protected by authority. They must survive the world. This is why a wrong anomaly can still be part of progress. If a strange particle signal fades, scientists learn where not to look, or how the detector behaves, or which background was underestimated. The absence becomes information. The failed clue redraws the boundary of what is possible. The map becomes cleaner, and if the signal does not fade, if it appears again, if another experiment sees it, if the statistical case grows stronger, if known explanations fail one after another, then the mood changes. A question mark begins to harden into evidence. The possible becomes plausible. The anomaly becomes a candidate for reality. That transformation is not sudden. It is built through repetition, through arguments, through peer review, through reanalysis, through long nights of checking whether anything ordinary could explain the extraordinary. The romance of science is often imagined as a single brilliant moment of discovery, but the truth is more patient. Reality is not usually revealed in one flash. It is separated from error layer by layer. There is beauty in that patience. A detector records a faint trace. Scientists hesitate. They doubt. They test. The signal remains. More data arrives. The pattern sharpens. Another experiment begins to agree. A theoretical framework starts to form around it. The strange becomes less strange, not because it was ordinary, but because understanding has grown large enough to contain it. That is how a particle that should not exist becomes a particle that does exist, not through excitement alone, through survival. And this is why uncertainty should not weaken the story, it should deepen it. The possibility that the discovery is wrong is not a distraction from science. It is the condition that makes science trustworthy. Without the chance of being wrong, there is no real test. Without skepticism, there is no real discovery. Without doubt, knowledge becomes fragile. A strange signal stands at the threshold. On one side is noise, on the other side is new physics. Between them is the method. The method is not glamorous. It is careful, repetitive, sometimes frustrating, and often slow. But it is one of the most powerful tools human beings have ever created. It allows us to listen to the universe without simply hearing what we want to hear. It allows us to turn uncertainty into structure. It allows us to approach truth without pretending we already possess it. So, if a particle that shouldn't exist appears in the data, the honest response is not immediate belief, it is attention, careful attention, because maybe the signal is a mistake. Maybe it is noise. Maybe it is a known process wearing an unfamiliar mask, or maybe it is the first trace of something real, something that has always existed beneath the surface of the known world, waiting for instruments sensitive enough and minds skeptical enough to recognize it. That combination matters. Sensitive enough to notice, skeptical enough to trust. The universe does not give up its secrets easily. It leaves hints, traces, and patterns that can deceive as well as reveal. Science is powerful because it knows this. It does not treat every mystery as a miracle. It asks the mystery to remain. A particle that should not exist must pass through doubt. And if it survives, then doubt will not have weakened the discovery. Doubt will have made it real. Reality does not promise to fit inside the theories we build for it. It never has. Long before there were equations, laboratories, detectors, or names for particles, the universe was already doing what it does. Fields were evolving, matter was forming, light was traveling, stars were igniting, galaxies were gathering. The deep structure of nature existed before any mind appeared to describe it. Our theories do not command reality, they follow it. That is worth remembering whenever science meets something unexpected. A strange signal in a detector does not mean the universe has broken. An unusual decay does not mean physics has failed. A possible particle outside the known catalogue does not mean reality has made a mistake. It means our understanding has reached a place where the map may no longer be complete, and that is not a weakness. That is the beginning of discovery. The Standard Model is one of the most powerful maps human beings have ever created. It describes the known particles of matter, the forces that bind and transform them, and the field that helps explain why many particles have mass. It has predicted results with extraordinary accuracy. It has survived experiments that pushed matter to extremes. It has allowed scientists to understand processes hidden far beneath the surface of ordinary experience. It is not a guess. It is not a rough sketch. It is a deep and precise framework built from decades of measurement and correction. But even the best map is not the territory. A map can be accurate and unfinished. It can guide us across enormous distances, mark the mountains and rivers, and still end at a coastline no one has crossed. The fact that it works does not prove that nothing lies beyond it. Sometimes, the success of a map is what allows us to recognize its edges. The standard model has edges. It does not fully explain dark matter, even though dark matter appears to shape galaxies and cosmic structure. It does not explain dark energy, the mysterious driver behind the accelerating expansion of the universe. It does not fully unite quantum physics with gravity. It does not fully explain why neutrinos have mass in the way they do. It does not explain why matter survived over antimatter, allowing stars, planets, and living bodies to exist. These are not small omissions, they are openings. They are places where reality seems to be saying that the current language, powerful as it is, may not be the final language. This is why an unexpected particle matters, not because it instantly solves everything, not because every anomaly is a revolution. Most strange signals fade. Many turn out to be noise, background, detector effects, or misunderstood ordinary physics. Science knows this. That is why it doubts itself. That is why it demands repeated tests, independent confirmation, and evidence strong enough to survive skepticism. But if a signal remains, if it grows clearer, if it appears again under different conditions, then it becomes more than a curiosity. It becomes a question reality is asking back. What have you missed? What else is there? What deeper rule would make this signal make sense? Every major theory in physics began, in some way, with the realization that the old picture was not enough. The world once seemed made of solid objects obeying simple motion. Then, light, electricity, magnetism, atoms, radiation, relativity, and quantum mechanics forced the picture to expand. Matter was not what it first appeared to be. Space and time were not passive. Empty space was not truly empty. Particles were not tiny marbles. Forces were not invisible strings pulling across nothing. Reality became stranger, but also more coherent. That is the pattern. Science does not move forward by making the universe less mysterious. It moves forward by making mystery more precise. A vague mystery becomes a measurement becomes a pattern becomes a theory, and a theory, if it is good, eventually reveals the next mystery. This is why the phrase, "a particle that shouldn't exist," is so powerful, but also so easy to misunderstand. The particle, if real, would not be violating reality. It would be violating expectation. It would not be breaking nature's laws. It would be showing that our version of those laws was incomplete. Nature does not need to obey the categories we have named. It does not care whether a particle fits neatly into a table. It does not care whether a force has already been discovered. It does not care whether human beings feel ready for another layer. Reality simply is. And our task is to listen carefully enough to notice when it refuses to match our assumptions. There is something humbling in that. The universe is not built around human intuition. At the smallest scales, particles behave as probabilities, fields, and interactions that defy ordinary common sense. At the largest scales, invisible matter shapes galaxies, and space itself expands under the influence of something we still do not understand. Between the quantum and the cosmic, we live in the narrow middle, surrounded by a reality far deeper than our senses were designed to perceive. And yet, we can perceive it indirectly. That may be the most remarkable part. We build detectors underground to hear faint signals from particles that barely interact. We build accelerators to recreate tiny fragments of early universe conditions. We build telescopes to collect ancient light from galaxies formed billions of years before Earth existed. We compare, calculate, doubt, revise, and try again. We use fragile instruments and imperfect minds to study a universe that is older, larger, and stranger than anything human imagination could have invented alone. A strange particle signal is part of that effort. It is not just a technical detail in a laboratory. It is a moment where the hidden structure of reality may be pressing lightly against the edge of what we know. It may vanish with more data. It may become a lesson in caution, or it may survive, becoming the first trace of a new field, a hidden force, a dark sector, or a deeper principle waiting beneath the standard model. Either way, the search matters, because the search is how knowledge stays alive. A finished science would be a dead science. A universe with no unanswered questions would leave no room for discovery. But the universe we inhabit is not finished in our understanding. It still contains shadows. Not supernatural shadows, but scientific ones. Areas where evidence exists, but explanation has not yet caught up. Dark matter is such a shadow. Dark energy is another. Quantum gravity is another. The origin of matter is another. And somewhere among these shadows, a new particle might belong. Maybe it is the missing piece of a known puzzle. Maybe it is the first clue to a puzzle we have not yet learned how to ask. Maybe it is nothing at all. But the possibility reminds us that physics is not a closed book. It is a language still being written, with every experiment adding or revising a sentence. Reality may still be under construction, not in itself, but in our understanding of it. The universe is not becoming deeper because we discover more. It was always deep. We are the ones becoming aware of the depth. That awareness changes our place in the story. We are made of particles governed by laws we did not choose. We live on a planet built from ancient cosmic processes. We think with brains made of matter whose foundation is quantum. And with those brains, we try to understand the particles, fields, forces, and histories that made understanding possible. There is a quiet circular beauty in that. The universe produces matter. Matter produces stars. Stars produce heavier elements. Elements produce planets. Planets produce life. Life produces minds. And minds build machines sensitive enough to ask whether the known particles are all there is. A particle that shouldn't exist is not a violation of reality. It is a sign that our map may be incomplete. It is a small mark at the edge of the known world, reminding us that the deepest truths are not always the most obvious ones. They may arrive as faint traces, strange excesses, missing energy, or patterns that refuse to disappear. They may begin as uncertainty. They may pass through doubt. And if they survive, they may become the next language physics uses to describe the universe. Somewhere inside that missing space, the next version of physics may already be waiting. Not separate from reality, hidden within it, waiting for a signal strong enough to be trusted, and for minds patient enough to understand what it means. Good night, and see you in the next video.